This video is a presentation summarizing research in robotic motion planning. The work is simulation-based using Python, and it is primarily focused on a pre-processing motion planning algorithm, meaning it is used for a group of robots to plan trajectories from point A to point B without colliding with static obstacles, as well as without colliding with each other. This is as opposed to the online components of real-time control, real-time feedback using sensors, computer vision, LiDAR, for conflict resolution, as well as tracking of the optimal trajectory, where the optimal trajectory is returned by the motion planning phase that will largely be talked about in this video.
Okay, so Cody, you can get started.
All right. So as Dr. Zhu mentioned, I've been working on my master's thesis, and my focus has been on multi-robot motion planning algorithms, specifically simulation of a sampling-based algorithm. I've been at Penn State for my bachelor's and master's, and I've kind of had experience in the past spanning between software, hardware. So I'm really interested in that kind of interdisciplinary nature of robotics. So I just wanted to thank Dr. Zhu and Dr. Ray for letting me be a part of the Networked Robotic Systems Lab. And also thank Jack, who I worked pretty closely with in as I progressed through my research. So first today, I want to talk a little bit generally about motion planning, what some different types of them are and how to compare the different methods. And then what difficulties arise in the multi-robot scenario compared to the single robot problem. I'm going to talk specifically a lot about what's called the INASH trajectory algorithm and how that algorithm searches through a state space for some system and generates paths. And then talk about what my contribution was in implementing this algorithm and get into the details of how I did so. So overall, motion planning is the process of calculating collision-free trajectories to get a robot from one starting state to its goal state and calculating the corresponding control inputs to follow that trajectory. So this, of course, has varieties of applications. A classic example is Amazon robotics, shown on the bottom left here, or anything from in factory environments like that to on the road with autonomous vehicles. Intersection environments. And it's increasingly important with just the general increasing of autonomous systems in all of these different scenarios. So the way we're going to compare different motion planning techniques is through their completeness, meaning are they guaranteed to return a solution in finite time? The computational complexity, amount of time it takes to return a solution, the storage requirements, the actual cost of the trajectory solutions that are returned. So how optimal is it in terms of either energy or time? The practicality, meaning maybe it returns a solution for some number of robot systems, but is it applicable in a larger variety of robot dynamics? And then the scalability for multi-robot systems, especially in the context of the computational complexity and how that changes with more robots. So a couple of examples here. For one, there's a grid-based example shown here on the top right called cell decomposition. And this method kind of breaks down some state space into a series of cells, and basically either through the edges or some angle theta through our cells, it's going to form some path to the goal set. And that's a complete algorithm. However, and even if it looks kind of simple for a two-dimensional plane, as soon as you scale that to a larger dimension robotic system, it becomes, it takes a lot of storage and computational power. Sampling-based algorithms I'll be talking about most, so I'll leave that for the future slides. And artificial potential fields are another example that are a little bit more computationally simpler, but have the possibility of local minimum, meaning a robot might actually not reach the goal set. It might get stuck at some point within the artificial potential field, which is generating some repulsion from obstacles and attraction towards the goals. So sampling-based methods start with some random sampling of the state space. And through that, they form some series of discrete state values connecting the start to the finish. So in those connections, we form what's called either a tree or a graph. And each of these black points here are going to be referred to as vertices, and then a path will be from the starting point to the goal region. These algorithms are known to be relatively scalable to higher dimension robotic systems. They're probabilistically complete, meaning the probability approaches 1 that it will return a solution. And then between these discrete states, there's going to be some continuous trajectory solution. And a potential downside is that it's not always easy to calculate these optimal control solutions for all robotic dynamics. Some examples of these algorithms are listed here. And specifically in, I think around 2012, RRT star and RRG listed here were developed as asymptotically globally optimal algorithms. So this is a really important development in the field of motion planning. And I'll talk a little bit more on them on the next slide as well. I also wanted to mention that I found it really interesting. These algorithms are not limited to robotic motion planning or continuous systems. For example, I recently found a paper that actually applied RRT to a hybrid power system in responding to cyber physical fault responses. So the way that these trees and graphs are expanding in these algorithms differs a little bit from algorithm to algorithm. But as I mentioned, it starts with some random vertex. And then basically from the nearest vertex that's in the existing graph or tree, we are going to expand the graph from that point to our new point. And for a lot of these algorithms, you're going to have a steering procedure, which is returning some new vertex, which is basically some maximum norm value. Within my research, I used a Euclidean norm. And over a number of iterations, this tree will expand over a larger portion of the state space. Now, in some of these algorithms, there's connections drawn from all of the near vertices, whereas in other ones, it's only drawn to maybe the nearest vertex. The INASH algorithm that I worked with draws connections from all of the near vertices. So drawing from similarity to RRG, except in RRG, there's connections drawn in both directions, and this algorithm only draws connections in one direction. So here's some examples of these algorithms in action. These results shown on the right are from the research done at MIT in the development of RRT star. And as you can see, with a larger number of iterations, this path approaches the globally optimal path reaching the goal set. Now, those examples are kind of describing mostly for single robot examples, but branching into the multi-robot scenario, we can categorize these algorithms into 3 categories: centralized, decentralized, and prioritized. In the centralized scenario, there's a possibility of achieving social optimums, meaning minimizing the total sum of all costs of your robot paths, but it's extremely computationally intense. Prioritized methods basically allow higher priority robots to choose some path, and then robot to robot, the lower priorities will then choose their path. So it's computationally efficient and technically scalable with the robot number, but at the expense of low optimal paths for those robots. And both of those methods are going to be pretty unrealistic in competitive scenarios where you don't have a centralized computer or you can't prioritize your robots. So that led to a lot of development in decentralized methods, which are a bit more computationally efficient, scalable in the robot number. There's been a lot of kind of work on trying to make these more time and energy optimal. And this kind of sets up the motivation for the trajectory algorithm that I focused on. So this INASH trajectory algorithm works as follows here. Essentially, for every robot, you're going to initialize your starting point and your goal set. Where's the robot trying to go? And then upon every iteration, you're going to expand the graph as I described on some of the previous slides. And then you're going to check which robots have some feasible path. So we're going to define a robot as an active robot. Once a robot has a feasible path, it's considered active. And then for all of those active robots, we're going to call what's called the better response procedure and input basically the entire graph for that robot, as well as which paths the other robots have selected. Within that better response procedure, we're going to generate a list of all of the paths for that graph, so just for that one robot. And then we're going to check which of those paths are collision-free with the other robots, and then choose the next lower cost path from the list. So this algorithm was developed a couple of years ago, and the simulation results were a bit limited. So my focus was on kind of expanding those results. But in summary, these the outcome of the design of this algorithm is that we have a linear algorithm. It only increases linearly with the number of robots that you add to the system. And that can be proved pretty quickly, basically by noting that within some iteration of your algorithm, every robot has some finite list of paths, and the dominating computational procedure is the collision checking procedure. So that collision checking procedure is going to be called a maximum of Q times per additional robot in that iteration. Additionally, this algorithm converges to a Nash equilibrium, meaning rather than in a social optimum where we minimize the total cost, the total sum of all costs, in a Nash equilibrium, we're just minimizing the cost of one individual robot's path given the current path plan of those other robots. Additionally, it's an anytime algorithm, meaning once it converges to a Nash equilibrium, the robots can still continue to expand their graphs in future iterations. And if any robot finds a new lower cost path, the better response procedure will continue to iterate, and the robots will reassess, reconverge to a Nash equilibrium. So my contribution in this was to expand the simulation results. I created a Python simulator from scratch. I provided some much more thorough computational analysis and confirmed the linearity for a variety of more inputs, and I'll describe more about what that means. Applied this to a larger variety of test cases, increased the robot dynamics to a second order problem. The original algorithm only had first order dynamics, and a lot more complications arise when you increase the order of the robot dynamics. And then I improved a little bit upon the design by integrating with some other known methodologies. So I used what's called Pygame for my simulation environment. So basically a simple 2D way of drawing. And this is going to be pretty much necessary before getting into some of the more elaborate simulators like Gazebo, which is a 3D robotics simulator. And additionally, this is a bit more realistic on when simulating on one computer for a large number of robots as well. So first I want to describe the actual definition of a robot for my simulations. So I used what's commonly referred to as the double integrator. And basically this is some disk robot, some mass m, and there's two inputs, the force in the x and y direction. So we can define our state space as these four states, the x and y, position, and velocity. Additionally, I applied some hard constraints on both the control magnitude and velocity magnitude. So that leaves us with the following state equation. So I mentioned that between any discrete states, there needs to be a locally optimized solution. And that means that we're working with a fixed initial state, fixed final state, free final time problem. So I chose to solve this as a minimum time problem. And that means we're defining the cost just as the arrival time. Now, something to note here is that the X and Y directions of the robot are uncoupled. So that kind of allows a little bit of makes it a little bit easier to solve this optimal control problem. So in the derivation of the controller, we can use the definition of our cost function, J. And for a minimum time problem, that means our G of the state, U and T, is equal to 1. And we get the following Hamiltonian. If you haven't taken an optimization or optimal control class, this might not mean a ton, but basically this is a method of deriving the necessary conditions for an optimal controller, where P is our co-state in the dual problem and F is the state equation from the previous slide. Now, this would be a bit more complicated for a more complicated robot, but this becomes a bang-bang solution when looking at either the X or the Y direction individually. So my methodology in solving this was to solve two separate bang-bang problems, both the X direction and the Y direction. However, that gets a different arrival time in each of those directions. So we keep the one that has a larger arrival time and then resolve the other direction as a fixed final time problem. So for example, let's say the X direction has a larger arrival time, then we resolve the Y direction, finding some new control magnitude and a switch time to arrive at the same time. So I'm not going to step through every line of all of these equations, but I wanted to point out here that this is guaranteed to always return a solution. And given a fixed initial and fixed final state, the values for the switch time and arrival time and adjusted control magnitude can be calculated numerically directly in software. So I refer to this as the second part as sub-bang-bang, basically meaning the way I solved the second portion is by adjusting the control magnitude. So since it's not the maximum, I call it sub-bang-bang. So I mentioned that in the growth of these trees, it depends on finding the near or nearest vertex in a tree. However, conceptually, you can kind of just look at the tree and see where it is pretty quickly, but programmatically, it's a bit more complicated. And if I were to store all vertices in an array and loop through and calculate the distance to every single vertex, then that would become extremely computationally intense for a large number of vertices. And these algorithms operate once you get into thousands and thousands of vertices. So it's not really feasible to do that. So I implemented the KD tree as a sorting algorithm. So basically, the binary tree, where upon inserting a new point, you're going to compare one state value on every layer. And a little bit more of a visual on the bottom left of what that means in the actual state space. You're basically splitting this space into, with some hyperplane. And then upon, when you're actually looking for that near or nearest vertex, you can essentially eliminate entire regions of this KD tree. And it speeds up the processes a lot. So this is a little bit easier to visualize here in the bottom left in 2 dimensions, maybe not as easy in 4 dimensions. Implementing it, maybe took some time, but then switching from 2D to 4D programmatically was not a major difference, actually. Some results of that, we can see here that the KD tree made some really great improvements in the speed. So on the right side, you can see that like thousands of more vertices are being found in a given time frame. So these simulations are actually running simultaneously. So you can see how much faster this tree is actually expanding through the space. Something else that's important is the method of collision checking. So basically in my code, every obstacle and goal region is defined as a set of vertices. And then every edge can be defined as the line between two vertices. So I use the same collision checking procedure for both the goal sets and the obstacles, so basically just checking for the collision between two lines. The difference was for the goal set, in addition to checking whether there was a collision, I specifically calculated the intersection point. And that's important because that helps avoid having robots that achieve a goal set, but then kind of circle around and keep moving around the goal region before a point just so happens to land, within that region. Calculating the intersection point directly makes the code, the path end at that first intersection point. So I want to define quickly what, how I actually defined a path. And, the simplest method would be just to define it as a list of these discrete vertices. And that's what I did initially. However, there were some complications with that later on. So basically, it had to do with computations of calculating collisions with other robots in the continuous trajectories between discrete points. So basically, for this example on the bottom, if we have a list of vertices, and say vertex 0 has 3 children, and the second child is the one that ends at vertex 1 in the path, then I define a path not just as this list of vertices, but as a list of vertices and the number corresponding to each child. So for this first point, it would be storing vertex 0 and the number 2 referring to that second child. And that provided some interesting computational improvements when checking for those collisions in the continuous trajectories. I do want to note, maybe down the road when this is implemented in a more physical environment, that, maybe online conflict resolution might be better to rely a little bit more on that instead of calculating for collisions in these continuous trajectories, but it just kind of some trade-offs to think about. So once a robot has a graph or a tree, there's a path generation procedure to then take that and calculate a list of paths that end at the goal set for that robot. So basically, I input any points that have collided with the goal region, and through recursion, I traverse backwards through the tree to get to the robot starting point. Going in this backwards direction is important to avoid doing unnecessary traversal through paths that don't end at the goal region. And then because this is done recursively, I just had to parse through those arrays rather than having a list of paths. Just had to parse them and turn that into a single list of paths for a given robot. Something else I tried and kind of implemented here was when calculating paths for a given vertex, I would store that path list within the vertex. So for example, if I were to calculate the path ending at this point here shown, then eventually the path from the starting point to here would be stored in this vertex. And when I'm recursing in the next iteration, starting at this goal point, then I don't need to recalculate the path for this vertex because it's already stored. Now I'm interested to see a little bit more maybe on storage data and analyze that a little bit more thoroughly, but it did seem to make some improvements with my code. Additionally, there's something referred to as RRT connect. And this is basically taking RRT and applying it both from the starting point and the goal set of your robot. and those trees grow towards each other. And then a path can be formed in the connection between those trees. So I took that concept and I applied it to the INASH algorithm. And it seemed to work pretty well. I just had to be really careful about how I was doing that, because it's really important in this algorithm to not create any cycles in the graph, meaning no loops back to some vertex that's already in an existing path. So it was important to kind of keep track of which tree the vertices were a part of. And then, of course, because anything in tree 2 can have new parents at any iteration, then the storage functionality that I mentioned here doesn't really apply to this second tree. Because on any new iteration, tree 2, some vertex in tree 2 can have new paths leading to it. So in RRT Connect, it's useful for decreasing the time taken to find a path. And that was true for INASH as well. But additionally, there were some interesting things that I noticed with INASH where, because it only forms new vertices as children in the algorithm design, there were a lot of new paths being formed that were kind of just deviating from a point that was closer to the goal set. Occasionally you'd have points that were maybe further out that would eventually collide, but these would happen much more frequently. And for a case where if this was a multi-robot scenario, and let's say right here, a robot were to collide with this path, then this gray robot, it only has these path options, and all of those path options would still collide at that point. And it seems like this INASH Connect method would kind of provide some more variety where the paths could branch out early in the path, but also reconnect at some point closer to the goal set. So to give more of a multi-robot scenario example, you can see a lot more variety going on here, where the colors are maybe the most recently selected paths, and then in black, you can see paths that had been selected at some point in time during the algorithm. Now, something that you may have noticed here is that there's a lot of oscillating and squiggling, and that seems pretty non-optimal in the global sense. And that seems to be because of the velocity sampling being completely random. So for example, on the left here, we can see a robot that needed to move very far to the left. And from a position sampling standpoint, it worked out fine where there was a path formed towards the goal set. However, just by random chance, the velocity happens to sample completely positive. And a result of that is every time you solve that locally optimal problem, it results in a robot that is oscillating back and forth. And that's going to obviously add a lot of cost to your path. So I implemented some biasing of the velocity to help prevent that, and it seemed to work pretty well. For example, on the top right here, we see a situation where the robot had to move to the right. So I biased the velocity to be positive. And you can see in these bang-bang solutions in the velocity plot, so this is a plot of x velocity versus x position, you can see that when the velocity samples at each point are still positive, it eliminates all of these oscillations where the robot's moving left, moving right, moving left, moving right. Now, additionally, you kind of notice that there's still oscillation in the y direction. So I also provided a bias for situations where maybe the distance is not very different between goal set and starting point. So here the y distance is not very large. So I biased the y velocity to be near 0. So you can see this line compared to this line, this one's a lot flatter, and it provides improvements in the cost of your path. Additionally, I created this actual motion simulator. So a lot of simulators up to this point have just been drawing the path or drawing the tree of the formation. But I actually generated videos to show, once the paths are selected, just to kind of prove further that all the collision checking procedures, etc., are working properly. And you can see robots are avoiding the static obstacles, avoiding each other, and reaching their goal set. Of course, for larger robot numbers, it's not always perfect. This is an anytime algorithm, meaning if I were to just wait longer for a given simulation, it should continue to search for more optimal paths for each robot and achieve new Nash equilibrium. But there's kind of a limitation to simulating 10 robots in an algorithm that's designed specifically for distributed computing. So for here, for example, there's 10 robots. So in the real world, the idea is that this would be run on 10 different processors that I'm simulating on one computer. So it kind of limits how much my computer can handle. But at the end of the day, still was generally pretty successful in achieving these Nash equilibrium and having these robots reach their goal sets. So I was able to then automate some results for getting the computational data. And I collected data for 225 tests in total and recorded the total time it took to achieve the first Nash equilibrium for a given simulation. Now again, since this was done on a single computer, I defined the distributed time to reach Nash equilibrium as the ratio of the total Nash time on my computer divided by the number of robots. And we can see all of the raw data as well as the average drawn here on this red line. So this is kind of interesting because it seems like this red line is pretty linear to start. You kind of have to think about the terminology. So we already proved mathematically that the algorithm is supposed to be at most linear. But what that really means is within a given iteration, for some robot, if you were to hypothetically add a new robot to that simulation, it would only increase linearly. So the importance in this data is recognizing that, okay, maybe we can prove per iteration that it's linear, but what happens for a large number of simulations when you have new inputs, such as the random chance in your graph formation and where the starting and goal sets are for your robots. So having these occasional points in raw data that are above that linear line, it doesn't actually violate the linearity proof. And it still kind of provides us evidence that, okay, on average, when we simulate this 225 times, it's a linear algorithm. And to confirm that this line is actually linear, I took this a little bit further and first plotted an average where at each point, it was the average between I minus 1, I and I plus 1. So for example, at point 10, it was the average Nash time between point 9, 10, and 11. So we can see this looks a bit more linear. And then to confirm that further, I took the second difference of this equation, and you can see that that always remains around 0. Now, I simulated up to 15 robots, and beyond that on my computer would be pushing it. 15 was getting pretty close to pushing it on what I was working with, but for the 0 or for 1 through 15 robots, it definitely seemed to provide some promising results on the computational complexity. So in summary, the iNash trajectory was successfully implemented for the 4-dimensional double integrator disk robot. It was noticed that additional collision checking difficulties were arising when incorporating those higher dimensions, so the velocity sampling. Although I mentioned, maybe it's possibly better to keep the collision checking only to discrete vertices and maybe rely more on online conflict resolution. There's kind of different methods there. Oscillation was a new problem upon expanding sampling into more dimensions. And velocity biasing was a simple kind of partial solution to that oscillation problem. although, maybe if you were to have higher actuator limits, maybe that would limit the amount of oscillation as well. So that's something to think about in the more practical sense in the future, at least. The KD tree was implemented, and that seemed to do a really good job of speeding up the algorithm. And that's a known methodology, but was applied successfully here. The extend procedure was kind of noted that seems to be at least a little bit of a limiting factor. Because, so on one hand, the extend procedure was chosen very specifically to be similar to RRG, but it couldn't be chosen as RRT star or RRG specifically in the design of the algorithm, just in terms of the theorems and guaranteeing convergence. So it was definitely chosen specifically, but if there is any method of improving that extend procedure, that would be definitely beneficial. And computational complexity was verified to be linear with robot number on average. So I've kind of mentioned a few of these just in that last slide too, but possible next steps are going to be essentially either pushing closer to application of these simulations, or I have a couple of more theoretical options listed here too. So maybe resolving the local problem for more elaborate robot dynamics. Maybe sending discrete path points to a 3D simulator, such as shown on the top right here. Maybe moving into the INASH policy algorithm, which is essentially the feedback control version of the trajectory algorithm. Maybe you'll analyze a more elaborate solution to the biasing problem. So I've seen some papers that applied neural networks to learn biases for position sampling. Maybe there's a possibility in using this for velocity biasing. So rather than just position for finding a path sooner, it could be velocity for improving a path cost. And then, if we were to implement on physical robots, we might get a better sense for distributed computing results since the simulations are being run on one system. So that's about what I have for today. So just want to thank everyone for listening. And if anyone has questions, of course, I can take those.
Okay, so any question from the audience?
I have a question.
Sure.
On page 11.
Yeah.